The law of conservation of energy states that energy cannot be created or destroyed, only transformed from one form to another within a closed system. Let's observe this fundamental law in action, where energy transforms without being created or lost. Light fixture. When a table lamp is switched on, the electrical energy is transformed into light energy, demonstrating the principle of energy conservation. Dry wood. Burning dry wood converts chemical energy into heat and light energy, illustrating the conservation of energy. Loudspeaker. Turning on a loudspeaker converts electrical energy into sound energy in accordance with the conservation of energy. Food. When food is consumed, the chemical energy it contains is converted and conserved through metabolic processes, exemplifying the principle of the conservation of energy. Chair. When a chair is pushed with the hand, the potential energy of the chair is transformed into kinetic energy, demonstrating the conservation of energy. Car accident. When a moving car hits a stationary car, the kinetic energy of the moving car is transferred to the stationary car, showcasing the conservation of energy in action. Torch. Switching on a torch converts electrical energy into light and heat energy, highlighting the principle of energy conservation. Ball. As a ball rolls on a ramp, the potential energy it initially possesses is gradually converted into kinetic energy in accordance with the conservation of energy. Microwave oven. When a microwave oven is switched on, the electrical energy is transformed into heat energy, demonstrating the principle of energy conservation. Dynamite. When a dynamite explodes, the stored chemical energy undergoes a rapid transformation, releasing a surge of kinetic energy, thus demonstrating the principle of energy conservation. Mango. When a mango falls from a tree branch, the potential energy it possesses while hanging from the branch is converted into kinetic energy as it descends, in accordance with the principle of energy conservation. Drum. When a drummer strikes the drum, the mechanical energy of the drumstick is converted into sound energy, showcasing the conservation of energy. Light bulb. The glowing of a light bulb signifies the conversion of electrical energy into light energy, illustrating the principle of energy conservation. Generator. Activating a generator converts mechanical energy into electrical energy, highlighting the conservation of energy in action. Hydropower. In hydropower plants, the potential energy stored in water at a higher elevation is harnessed and converted into electrical energy, exemplifying the conservation of energy. Nuclear power plant. Within nuclear power plants, the intricate process of converting nuclear energy into electrical energy takes place, showcasing the principles of energy conservation. Hand rubbing. When vigorously rubbing hands together, the mechanical energy exerted is transformed into heat energy, aligning with the fundamental concept of energy conservation. Fossil fuel. The combustion of fossil fuels results in the conversion of chemical energy stored within them into heat energy in accordance with the principle of energy conservation. Moving bike. When brakes are applied to a moving bike, its mechanical energy dissipates and transforms into heat energy in accordance with the principle of energy conservation. Electric motor. When an electric motor is activated, the electrical energy supplied to it is efficiently converted into mechanical energy, exemplifying the conservation of energy. Photosynthesis. During photosynthesis, light energy is efficiently transformed into chemical energy, demonstrating the principle of energy conservation. Mobile phone. During the charging of a battery, electrical energy is transformed into chemical energy, adhering to the principle of energy conservation. Newton's cradle. Within Newton's cradle, the potential energy of one ball is transferred and converted into kinetic energy as it collides with the adjacent balls, showcasing the conservation of energy in action. So we've covered enough examples to understand the law of conservation of energy. Let's now explore the equation and solve some practice problems. The law of conservation of energy equation is expressed as KE initial plus U initial is equal to KE final plus U final, where KE initial is the initial kinetic energy, U initial is the initial potential energy, KE final is the final kinetic energy, and U final is the final potential energy. This equation illustrates the conservation of energy in a closed system, showcasing the equilibrium between initial and final kinetic and potential energy. Let's solve some practice problems to apply and understand the law of conservation of energy equation. A 5 kilogram sphere, initially at rest, is positioned on the edge of a cliff at a height of 30 meters. The sphere rolls down the hill. Calculate the velocity of the sphere when it is at a height of 15 meters. Assume the gravitational acceleration as g equals 9.81 meters per second square. Note down the data, insert the values into the formula, and determine the velocity as needed. The mass is given as m equals 5 kilograms. Since it is at rest, write the initial velocity as v initial equals 0 meters per second. The initial height is given as h initial equals 30 meters. We have to calculate the final velocity, so v final is equal to question mark, and the final height is h final equals 15 meters. The value of gravitational acceleration is given as g equals 9.81 meters per second square. Insert these values into the equation KE initial plus U initial equals KE final plus U final. We will simplify it as half mv initial square plus mgh initial is equal to half mv final square plus mgh final. The m will get cancelled. So, writing in a more simple way, half v initial square plus gh initial is equal to half v final square plus gh final. Now, v initial equals 0 meters per second, so write 0 plus 9.81 multiplied by 30. We have to find v final, keep it as it is, and write is equal to half v final square plus 9.81 multiplied by 15. Therefore, the calculation becomes 294.3 is equal to half v final square plus 147.15. Write in the next line, half v final square is equal to 147.15. Shift half on the right side, so we get v final square is equal to 294.3, and therefore the value of v final becomes 17.15 meters per second. Therefore, the velocity of the sphere when it is at a height of 15 meters is approximately 17.15 meters per second. Let's take one more practice problem. A 25-gram balloon is floating in the sky at a height of 60 meters above the ground and is descending with a velocity of 2 meters per second. Determine the velocity of the balloon when it is at a height of 10 meters. Use the value of gravitational acceleration as g is equal to 9.81 meters per second square. Use the provided data, input the values into the formula, and find the velocity as requested. The mass of the balloon is given as m equals 25 gram. On dividing it by 1,000, the value becomes m equals 0.025 kilograms. The initial height of the balloon is given as h initial is equal to 60 meters. The initial velocity is given, but the balloon is descending, so we will write the initial velocity as v initial equals minus 2 meter per second. We have to calculate the final velocity, so v final equals question mark, and the final height is h final equals 10 meter. The gravitational acceleration value is given as g is equal to 9.81 meter per second square. Place these values into the equation ke initial plus u initial is equal to ke final plus u final. First, simplify the equation as half mv initial square plus mgh initial is equal to half mv final square plus mgh final. The m will get cancelled, so write in a more simple form as half v initial square plus gh initial is equal to half v final square plus gh final. Write as half multiplied by minus 2 square plus 9.81 multiplied by 60. Now v final equals question mark, so write that v final part as it is and write is equal to half v final square plus 9.81 multiplied by 10. The calculation further becomes 2 plus 588.6 is equal to half v final square plus 98.1. So 590.6 is equal to half v final square plus 98.1. Subtract the value and write as half v final square is equal to 492.5. Move half on the right side, so v final square is equal to 985. And finally, we get the value of v final as 31.38 meter per second. Hence, the velocity of the balloon when it is at a height of 10 meter is approximately 31.38 meter per second. So that's a wrap on the law of conservation of energy. If you found this explanation helpful, press the like button, share the video with your pals, and subscribe for more knowledge.